Hello everyone! This video is entitled Polyatomic Ions. In this lecture, I will explain what polyatomic ions are, walk you through the process of writing out the chemical formulas of ionic compounds that contain polyatomic ions, and show you how to properly name ionic compounds that have these particular ions within them. If you have not yet watched my video on transition metals, it is recommended that you do so first to fully understand this material. You can find a link to that video in the description below. Okay, let's get started.
Polyatomic ions consist of two or more different nonmetal atoms, which are joined by covalent bonds and have an overall charge. There are many different kinds of polyatomic ions, but 5 primary types of polyatomic ions are most commonly used in science and are seen the most often in scientific text. A mnemonic has been created to assist students in remembering these 5 primary types of polyatomic ions and how to write them out. The mnemonic is Nick, the camel, ate a clam for supper in Phoenix. For this mnemonic to serve its purpose, it must be written out correctly and read in a very particular way. The underlined letters in each word represent the symbol of the element that is used to name the polyatomic ion. The consonants in each word represent the number of oxygen atoms present within the polyatomic ion being represented. The vowels represent the number of negative charges on the polyatomic ion. Each polyatomic ion consists of the name of the element with the ending "ate", and that is why the word "ate" is in the mnemonic. The first word of the mnemonic is Nick. The underlined letter is N, representing the element nitrogen. There are 3 consonants to this word and 1 vowel. So how do we put it all together? Well, the chemical formula for the polyatomic ion will start with the symbol N. The consonants represent the 3 oxygen atoms in this polyatomic ion. The number of vowels represents a 1 negative charge on the ion. The name of this ion is nitrate, and the ending "ate" again is represented in the mnemonic. The second word in the mnemonic is camel. The underlined letter is C, representing the element carbon. There are 3 consonants in this word and 2 vowels. So how do we put it all together? Well, the chemical formula for the polyatomic ion will start with C. The consonants represent the 3 oxygen atoms in this polyatomic ion, and the 2 vowels represents a 2 negative charge on this ion. The name of this polyatomic ion is carbonate. The third word in the mnemonic is clam. The underlined letters are Cl, representing the element chlorine. There are 3 consonants in this word and 1 vowel. So how do we put it all together? Well, the chemical formula for the ion will start with Cl. The 3 consonants represents the 3 oxygen atoms in the ion, and the 1 vowel represents the 1 negative charge on this compound. The name of this polyatomic ion is chlorate. The fourth word in the mnemonic is supper. Be sure to spell it correctly with 2 P's, otherwise you've spelt super. The underlined letter is S, representing the element sulfur. There are 4 consonants in this word and 2 vowels. So how do we put it all together? Well, the chemical formula will start with S. The consonants represent 4 oxygen atoms inside this ion, and the 2 vowels represents a 2 negative charge on this compound. The name of this polyatomic ion is sulfate. The last word in the mnemonic is phoenix. The underlined letter is P, representing the element phosphorus. There are 4 consonants and 3 vowels in this word. So how do we put it all together? Well, of course, the chemical formula for the polyatomic ion will start with P. The 4 consonants represents the 4 oxygen atoms inside this ion, and the 3 vowels represents a 3 negative charge on this compound. The name of this ion is phosphate. Now, it's worth repeating, the mnemonic only helps you remember the 5 primary types of polyatomics. However, there are additional polyatomic ions that you will need to know. Below are 2 more polyatomic ions that don't follow the rules of the mnemonic but are very important to know. The ions are the ammonium ion and the hydroxide ion. These 2 ions will become incredibly important when discussing acid-base interactions. And so, although there are other polyatomic ions that you will need to know, the ions mentioned to this point are the most often cited in scientific texts, and that's why I focus so much on those particular polyatomic ions. What I find personally interesting about polyatomic ions is not only that there are so many different types of polyatomic ions, but within each type there are many variations. These variations can be caused with the addition or subtraction of particular types of elements. One such variation comes from the addition of hydrogen ions to a polyatomic structure. Many polyatomic ions can form bonds with 1 or more hydrogen ions, creating hydrogen polyatomic ions. When a hydrogen ion bonds to a polyatomic ion, its positive charge neutralizes 1 of the negative charges in the polyatomic structure. The example I have here is a hydrogen ion being added to a sulfate ion. You can see that sulfate has a 2 negative charge, and when 1 hydrogen ion is added to this sulfate ion, the positive charge of the hydrogen ion cancels out 1 of the negative charges on the sulfate ion, leaving behind a hydrogen sulfate ion with a 1 negative charge. A hydrogen ion can be added to any polyatomic ion that has a negative charge. The number of hydrogen ions that can bond to a particular type of polyatomic ion is dependent on how many negative charges that polyatomic ion has. For my second example, I have hydrogen ions being added to a phosphate ion. You can see that the phosphate ion has a 3 negative charge. Now that means that you can add as many as 3 positive hydrogen ions to this phosphate ion to get rid of those negative charges. If I were to add 2 hydrogen ions, those 2 positive charges will cancel out 2 of the negative charges on the phosphate ion, leaving behind 1 negative charge on the new type of hydrogen phosphate ion. This particular type of hydrogen phosphate ion would be called dihydrogen phosphate ion. The di represents the 2 hydrogens that have been added to this 1 phosphate ion. Polyatomic ions that contain oxygen are known as oxyanions. Oxy to indicate the presence of oxygen within the polyatomic structure, and anion to designate that that polyatomic structure has an overall negative charge. In speaking of variations, the elements that form the root of polyatomic ions can actually form more than one kind of polyatomic ion. The example I have here is chlorate. Now, chlorate is primarily based off of chlorine. We call that the stem of the polyatomic ion. Now, chlorine can form many different kinds of variations with oxygen to form different kinds of oxyanions. All the variations formed around this element have the same charge, but only differ in the number of oxygen atoms. Changes to the prefix and suffix of these ions are made to differentiate between different ion variations. Now, bear in mind, when I say suffix, I mean the ending of the name, and prefix, the start of the name. The naming system for these polyatomic ions are as follows. If one oxygen atom is added to the primary polyatomic ion, and when we say primary, we mean the main type, one of the 5 primary polyatomic ions I taught you at the beginning of this package. And so in this case, chlorate. If I add one oxygen, I have to add the prefix to the name PER, per. And so this ion would now be called perchlorate. And you can see that the only variation here is the addition of one more oxygen atom. If one oxygen atom is removed from the primary ion, I change the ending of the ion name to ITE, ite. And so the primary ion has lost one electron, and it now has the name chlorite. If 2 oxygen atoms are removed from the primary ion, you add the prefix HYPO, hypo, and you change the suffix to ite as well. And so in this case, the primary ion has 3 oxygen atoms. If I reduce it to 1 oxygen atom, I now call the ion hypochlorite. Now, it's important to note that these variations and the same naming system can occur to many different types of polyatomic ions, as you'll see in the coming slides. So as I was saying, these variations can exist in many different types of polyatomic ions. Here we have phosphate. Let's use this naming system to identify the different variations that can occur within the phosphate structure. If I were to add one oxygen to phosphate, I would get perphosphate. Notice that the only thing that has changed here is the number of oxygen atoms. The charge has remained the same, and that's incredibly important for you to take note of. The charge on these ions never change. Within all the variations of phosphate, you will always have a charge of 3 negative. And so, of course, the phosphate ion had 4 oxygen atoms, and now we have the perphosphate ion that has 5 oxygen atoms. We designate this particular variation with the prefix per. If we remove one oxygen atom, we go back to phosphate. Now let's see what happens when one oxygen atom is removed. We get phosphite. Notice again that the only change that has been made here is to the number of oxygens. The charge of 3 negative remains the same. Phosphate had 4 oxygens, while phosphite has 3 oxygens. The ending ATE has been changed now to ITE to differentiate between these two types of variations. Now, what if I were to take one more oxygen away from phosphite? I would get hypophosphite. Now, for me to arrive to hypophosphite, I needed to remove 2 oxygens from the primary ion being phosphate. And so now I have PO2 3 negative. Remember, the charge has not changed. You'll notice that I cannot remove any more oxygen. The reason being is because I've removed the maximum number I can from this type of polyatomic structure. Although it looks like I can remove another one, the second I add the prefix hypo, that indicates that's the maximum number of oxygens that can be removed from this type of polyatomic structure.
This is a table of all the polyatomic ions and polyatomic ion variations that you should know. It's prudent that you're able to look up these polyatomics quickly when trying to answer questions. And so, of course, the more practice questions you do, the quicker you'll be at answering questions when faced with assessments. So do as many practice questions as you can so that you're better prepared.
Chemical formulas containing polyatomic ions. The steps for writing the chemical formulas of compounds containing polyatomic ions are the same as those for binary ionic compounds. To review, the 7 steps are: identify the metal and the nonmetal, write the symbols, write the charges on those symbols, cross the charges over from top to bottom, remove the charged symbols, simplify the numbers and remove the ones, and write the chemical formula. Let's try some practice questions. Here we have iron 2 arsenate. The first thing we need to do is we need to identify the metal and the nonmetal. Obviously, iron is the metal and arsenate is the nonmetal component. I will say, many students find it difficult to find arsenate in the polyatomic ion chart. Some will take a very long time to locate it, and others will not locate it because they have spent their time looking for arsenate in the periodic table. Clearly, they will not find it there because arsenate is not an element. It is a polyatomic ion. It begs to reason that the more practice you have writing out compounds with polyatomic ions, the easier it will become to find those ions when answering questions on assessments in the future. The next step is to write the symbols for the metal and the nonmetal component. I know from the periodic table that iron is symbolized by Fe. And I know from the polyatomic ion chart that arsenate is symbolized as AsO4. Next, write the charges. The Roman numeral 2 in the name indicates that iron will have a charge of 2 positive. And I know from the polyatomic ion chart that arsenate will have a charge of 3 negative. Next, cross over the charges from top to bottom. Now you can see here why it's so important to include brackets around your polyatomic ion. This is so that the number for the charge that you have crossed over does not get confused with the number of atoms of a particular element in your polyatomic ion. So it keeps these two numbers separate. Next, remove the charge symbols. In step 6, simplify the numbers and remove the ones. Now, I must make it crystal clear. The numbers that are to be simplified are only the numbers that came from the charges. The numbers within the brackets are never simplified. They are never touched when writing out a chemical formula. And so these numbers are never ever included when simplifying for a chemical formula. And so obviously I cannot simplify the 3 and the 2 here, and so I write my chemical formula as Fe3 open bracket AsO4 close bracket 2. For our next example, we have magnesium oxalate. The first thing we need to do is we need to identify the metal and the nonmetal. And so obviously magnesium is the metal and oxalate is the nonmetal component. Next, write the symbols. And so magnesium is symbolized as Mg, and oxalate from the polyatomic ion chart I know is symbolized by C2O4. Now write the charges. Because of its placement on the periodic table, magnesium is always going to be 2 positive. And from the polyatomic ion chart, I know oxalate will have a charge of 2 negative. Cross the charges over from top to bottom. Remove the charge symbols. And now simplify the numbers. Now keep in mind, I put brackets around oxalate to keep the 2 of the charge separate from the number of atoms of a particular element within the ion. And so now that I'm simplifying, I can actually remove those 2's and remove the 1's that have replaced them. And so you can see that the bracket has disappeared. The reason the bracket has disappeared is because when I go to write my chemical formula, I put it together and I do not need to put the brackets because I only have one oxalate ion connecting to one magnesium ion. And so I get MgC2O4. Here are some practice questions that may help solidify the naming system for polyatomic ions. As always, the answers to these questions have been provided to you in the slide. I recommend that you try to answer these questions yourself and only use the answers as a reference to make sure you're doing these questions correctly. And with this slide, I conclude this package and this lecture. I hope everything I discussed today made sense. Thank you for listening. All the best.